Okay, so this is problem 1. And in this one we've got a composite rod with length L, which is made up of two materials of length L1 and L2. So the length of the rod is equal to L1 plus L2. And material 1 is L1. It's got some thermal expansion coefficient alpha 1, and L2 has some thermal expansion coefficient alpha 2. So we know that the change in length of anything is equal to alpha times the initial length times the change in temperature. So our thermal expansion coefficient is equal to the change in length over the length times delta T. And what we're asked for is to come up with a thermal expansion coefficient for this composite rod. So we know that once it changes in temperature, the change in length is going to be equal to the change in length of part 1 plus the change in length of part 2. So this will be alpha 1 times L1 times delta T plus alpha 2 times L2 times delta T. So now we've got an expression for the change in length, which we can substitute into this equation up here. So our composite alpha is given by alpha 1 L1 delta T plus alpha 2 L2 delta T over L delta T. So these delta T's cancel out, and so we've got alpha 1 L1 plus alpha 2 L2 over L. So that's our composite alpha. So that was part A. In part B, we're now given some numbers. We're told that the length of the rod initially was 52.4 centimeters, and we're told that the composite alpha is equal to 13 times 10 to the minus 6 per degrees Celsius. And so we can write this as 1.3 times 10 to the minus 5 per degree Celsius. And we've got alpha 1. We'll call this steel because we're not told which one's 1 and which one's 2. So this will be steel. And this is equal to 1.1 times 10 to the minus 5 per degree C. And alpha 2, this is the brass, is equal to 1.9 times 10 to the minus 5 per degree C. And we're asked, well, what's L1, the length of the steel, and what's L2, the length of the brass. Okay, so we'll need to write down some equations to say what we know. So we know that the length is equal to 52.4 centimeters, and that's equal to L1 plus L2. So let's call this one equation 1. We also know from this equation that we've got alpha L is equal to alpha 1 L1 plus alpha 2 L2, and we know what these alphas are and this L is. So alpha, that's equal to 1.3 times 10 to the minus 5 times L, which is 52.4, and that's equal to alpha 1, which is 1.1 times 10 to the minus 5 L1 plus 1.9 times 10 to the minus 5 L2. Now all these times 10 to the minus 5s cancel off, which is why I initially rearranged this one to give it to a power of minus 5. And so we've got 1.3 times 52.4. That is equal to 68.12, and this is equal to 1.1 L1 plus 1.9 L2. So let's call this equation 2. So now we've got two equations and two unknowns. So we can solve these simultaneously. So let's rearrange equation 1. We can write this as L2 is equal to 52.4 minus L1. And now what we can do is substitute this into this equation here. So now I've got 68.12 is equal to 1.1 L1 plus 1.9 times 52.4 minus L1. Okay, so we've got 1.1 L1, minus 1.9 L1. If we move that over to this side, on this side we've got minus 0.8 L1. So over here we've got 0.8 L1. And that is equal to 1.9 times 52.4, which is 99.56, minus R 68.12. So this is equal to 31.44. So now I can solve this, just divide by 0.8, and I get L1 is equal to 39.3 centimeters. So that's of steel. And then L2 is equal to 52.44 minus the 39.3, which is equal to 13.1 centimeters of brass. And that's how we solve that problem. This is problem 2. So in this problem, we're told that the initial temperature is equal to 20.000 degrees C of an unknown metal. Its initial length is equal to 12.000 centimeters. And when it's heated up to 120 degrees, so the final temperature is 120.000 degrees C, then its final length is equal to 12.016 centimeters. And in part A, we're asked to calculate the linear expansion coefficient of the metal. So we know that the change in length is equal to alpha times the initial length times the change in temperature. So this tells us that alpha is equal to the change in length over the initial length times the change in temperature. So substituting in the change in length, it's 12.016 minus 12.000, so there'll be 0.016. Divided by the length, which is 12. This is in centimeters and this is in centimeters, so those units cancel out. We didn't need to convert to meters, times the change in temperature. So that's the 120.000 minus 20.000, which is 100. Okay, so we're doing 0.016 over 12 times 100. And solving that, we end up with 1.33 times 10 to the minus 5 per degree C. But then technically, since this difference here only had two significant figures, we should really give this to two significant figures. So 1.3 times 10 to the minus 5 per degree C, which is about the right order of magnitude for a metal. So that's good. Okay, part B, then what is the length of the rod at the freezing point of water? So we want to know the length at 0 degrees C. Okay, so we can work out the change in length as the temperature decreases from 20 degrees C down to 0 degrees C. So alpha we've got now is equal to 1.33 times 10 to the minus 5. The initial length, that's this 12 centimeters at 20 degrees C. The change in temperature, that's the final temperature, which is the 0 minus the 20. So solving that, we get a change in length of minus 3.2 times 10 to the minus 3. And as this was in centimeters, this is in centimeters. Okay, so that's the change in length. So we're asked for the length at 0 degrees C. So that'll be the initial length, the 12, plus the change in length, which is a negative number. So it's minus 3.2 times 10 to the minus 3 in this case. And so that is equal to 11.997 centimeters is the length of the metal at 0 degrees C. And then part C asks us what is the temperature if the length of the rod is now. So now the length is equal to 12.010 centimeters, and we're asked what's the temperature. So to get the change in temperature, we'll need to use the change in length over alpha times the initial length. The change in length, that's the final length, 12.010, and the initial length was the 12 centimeters. so this is just 0.010 over alpha, which is 1.33 times 10 to the minus 5 times the initial length, which is the 12.000. Okay, so solving this, we end up with a change in temperature of 62.7 degrees C, and we've got an initial temperature of 20 degrees C, so the final temperature is equal to 82.7 degrees C. Okay, so this is problem 3. So in this problem, we have a copper bowl. So the mass of the bowl is equal to 146 grams. It contains 223 grams of water. And both the bowl and the water are initially at 21 degrees C. And then a very hot copper cylinder. So the mass of the cylinder is equal to 314 grams is added, and this causes the water to boil, with 4.7 grams being converted to steam. So the mass of steam is 4.70 grams, and the final temperature of the entire system is equal to 100 degrees C. And in part A, we asked how much heat was transferred to the water. So we want to know the heat transferred to the water. Okay, so the heat transferred to the water does two things. It heats up the water and then it converts some of it to steam. So the amount that's needed to heat it up is given by the mass of water times the heat capacity of water times the change in temperature of the water. And then we need to convert the steam, so that's the mass of steam times the latent heat of vaporization. So now we'll need to look up some of these constants on the data sheet. So the specific heat of water is 4,186 joules per kilogram per Kelvin, or per degree C, it doesn't matter. And the latent heat of vaporization of water is equal to 2.26 times 10 to the 6 joules per kilogram. Okay, so now we can substitute in, we'll need our masses in kilograms. So the mass of the water is 223 grams, which is 0.223 kilograms, times 4,186, times the change in temperature of the water, which is the final temperature, 100 degrees C, minus the initial temperature, 21 degrees C, plus the latent heat of fusion. So this is, the latent heat. So that's the mass of the steam, 4.70 times 10 to the minus 3 to get it into kilograms, and then times 2.26 times 10 to the 6. Solving this on the calculator, we end up with 84,366 joules, which we can write as 84.4 kilojoules, and that's to 3 significant figures. So that's heat which the water is gaining. Now in part B, it says how much to the bowl. So now we want to know, well, how much heat's added to the bowl. The bowl doesn't change state at all, and so the heat added, it just goes into the specific heat changing its temperature. So we've got the mass of the bowl times the specific heat of copper times the change in temperature of the bowl. Now the specific heat of copper, we need to look that up. That is equal to 390 joules per kilogram per Kelvin. And so substituting in for the bowl, we've got 0.146 times the 390 times the change in temperature, which is the 100 minus 21. Solving this on the calculator, we end up with 4,498 joules. So we can write this as 4.50 kilojoules. Part C then says, what's the original temperature of the cylinder? Okay, so to work this out, we're going to need to make the assumption that no heat is lost from the system. So assume no heat is lost from the system. then we know that the heat transferred to the water and the bowl comes from the cylinder. So the heat from the cylinder plus the heat to the water plus the heat to the bowl is equal to 0. The cylinder will end up cooler, so it's going to be losing heat, so QC is going to be negative. But we can rearrange this to say QC is equal to minus QW minus QB, and we've got values for these things. And we also know that QC is equal to the mass of the cylinder times the specific heat of copper times the change in temperature of the cylinder, and that's equal to minus QW minus QB. So we can rearrange this equation and get that our change in temperature of the cylinder is equal to minus QW minus QB over mass of the cylinder times the specific heat of copper. Okay, so we can substitute in now. We've got minus 84.4 minus 4.50. Now this is all in kilojoules, so we times it by 1,000 to put it back into joules. Then the mass of the cylinder, we were told, was 314 grams, so that's 0.314 kilograms times the specific heat of copper, which is 390. So solving this, we end up with minus 726 degrees C. We're expecting a negative number because we just said we expected to end up colder than what it started at. Okay, so we've got delta TC, that's the change in temperature of the cylinder, which is the final temperature of the cylinder minus the initial temperature of the cylinder is equal to minus 726. And so the initial temperature of the cylinder is equal to the final temperature of the cylinder plus 726. And we know that everything ends up at 100 degrees C. So this is 100 degrees C plus 726 degrees C. And so that is equal to 826 degrees C as the initial temperature for the cylinder. This is problem 4. This one's actually a little bit tricky. Okay, so in case A, what I'll do before I start is I'm going to split the screen in half and we'll do case A here and case B on this side, just to make sure that there's room. So in case A, we've got K1 here, we've got K2 here, and then it goes through K1 again and K2 again. And in case B, up here we've got K2, and then we've got K1, and down here we've got K2, and here we've got K1. And just to make everything clear, let's color these different colors. So let's make this one green, red, that one can be green, and then we can have a blue one, and then we can have a yellow one. Just to make it, that'll help us a little bit later on. And each of these materials has some thickness, and we'll call that thickness delta xt, and they've all got the same cross-sectional area, A. And so in case A, the heat flows from this hot side here to this cold side here. Same thing in case B, hot side, cold side. And then we've got a junction in the middle. Now, for case A, because we've got the same material on both sides, this junction temperature is going to be the same everywhere. We'd expect it to drop by half the temperature from the hot side to the middle, and then from half the temperature again from the middle to the cold side. But it'll do that in both cases because we've got the same type of material on both sides. Whereas in case B, we don't have that. So we'll have one junction temperature up the top, TJ1 let's call it, and a different junction temperature, call it TJ2, down the bottom. Okay, so for case A, let's come up with an expression for how much heat flows through it. So hopefully you can see that some of the heat will flow through the top, some of the heat will flow through the bottom, and so the total amount of heat flow is going to be equal to the top plus the bottom. So let's start by working out the heat flow through the top. Now, hopefully you remember one of the important rules we saw. We saw that we had to have heat flow which was constant throughout a bar. So if we had a bar which was made of two materials, then the heat flow through this part was the same as the heat flow of that through that part. Otherwise, we'd end up with a hot or a cold spot in the middle. So let's call the heat flow through this red one. Let's call that P, and we know that that is equal to Ka times the change in temperature. So the change in temperature is, in this case, Th minus Tj, and that's over the thickness, which is T. And that has to be equal to the heat flow through the green one, which is equal to Ka. Now, in this case, the hot side is the junction temperature, Tj minus Tc over T. Okay, so hopefully you can read that in the green there. Okay, so now what I can do is solve this to work out the junction temperature to start with. And so solving this for the junction temperature, these cancel. And so we have Th minus Tj is equal to Tj minus Tc. So Th plus Tc is equal to 2Tj, which tells us that the junction temperature Tj is equal to a half Th plus Tc, which we vaguely mentioned before when we said it should be the middle temperature in the middle. This is the average of the hot and the cold sides. So that's what it is all along there. The same would hold for K2. We just have here, these were actually K1s. For the bottom part, they'd be K2s. Okay, so the P through the top is equal to K1A times the hot minus the junction temperature, which is a half times Th plus Tc over the thickness. And so that is equal to K1A. Now this is Th minus a half Th, so that's a half Th minus a half Tc over T. So this is equal to K1A over, we can move this half out the front, so we'll end up with 2T times Th minus Tc. Now for the bottom half, the working is going to be exactly the same, except that now our thermal conductivity is K2 instead of K1. So this will be K2A over 2T Th minus Tc, and so P total will be equal to K1A over 2T Th minus Tc plus K2A over 2T Th minus Tc, and almost everything here is a common factor, so we can write this as A times K1 plus K2 times Th minus Tc over 2T, and that's our total heat flowing through this setup here. Okay, so now we need to work out what the heat flow in case B is, and then we'll be able to compare them. Okay, so let's just start with the heat flow through the top. We know that the heat flow through the red is equal to the heat flow through the green. So let's write those out again. So we've got the heat flow through the red is equal to K2A on T, and the temperature difference, that's Th minus Tj1. And we know that that's equal to the temperature flow through this green one, which is K1A over T Tj1 minus Tc. Okay, so like we did before, let's solve this to work out the junction temperature, TJ1. So the A's and the T's will cancel each other out, and we'll end up with K2TH minus K2TJ1 is equal to K1TJ1 minus K1TC. And so pulling the junction temperature out as a common factor, we have TJ1, K1 plus K2. That's moving this over to this side and pulling TJ out. And then we need to move this over to this side. So then we've got K2TH plus K1TC. And so this tells us that the junction temperature is equal to K2TH plus K1TC over K1 plus K2. Okay, so now we're going to solve for the heat flow through the top. So the heat flow through the top is equal to K2A on T times TH minus the junction temperature, which is K2TH plus K1TC all over K1 plus K2. Okay, so what I'm going to do now is times both my numerator and my denominator by K1 plus K2. That'll cancel out this factor on the bottom here. And so this gives me K2A TH times K1 plus K2. So that's THK1 plus THK2. Now this cancels that, so then I have minus K2TH plus K1TC all over T K1 plus K2. Okay, so that K2TH cancels this one, they're the same, and so this is equal to K2A THK1 plus K1TC over T K1 plus K2. Okay, that's through the top. Now, we can just argue that the order of these two things shouldn't matter. It'll lead to a different junction temperature, but we've essentially got the same materials, just in opposite orders. And so the heat flow through the bottom is going to be the same as the heat flow through the top. And so the total heat flow is equal to 2K2A. Now here K1 is actually a common factor, so let's pull that out the front, and then we've got TH plus TC over T K1 plus K2. If you're not happy with the argument for doubling it, then you can work through the same thing for the bottom, and you will end up with the same expression. Okay, so now we're told, the point of the question was, well, which one's greater if K1 is not equal to K2? So probably the easiest way to solve this is just let's substitute in numbers and see which one's bigger. Is this bigger or is this bigger? So if we let K1 equal 1 and K2 equal 2, in this case for A, P total is equal to A times K1 plus K2, so that's 1 plus 2, that's 3, times TH minus TC over 2T. In this case, we'd have 2 times K2, which is 2, so 2 times A, K1, that's 1, times TH plus TC over T times 3. So let's just let TH equal 100 and TC equals 0. In this case, this would be 100 minus 0, so that would be equal to 300A over 2T. And in this case, this is 4, So we'd have 4A times 100 plus 0. So that would be 400A over 3T. A on T is a common factor. So this is 150 A on T. This one is 133 A on T. So this one, case A, is bigger. So case A has the larger heat flow, which is really intuitively what you'd expect, because if one of these was very, very low, it would let through a lot of heat, and so you'd expect having two really poor insulators together would leave you much colder if this was clothing than having a poor insulator paired with a good insulator. So this is problem 5, which is relatively straightforward. We're told that the initial height of a streetlight is equal to 7.6 meters, and that is measured at 18 degrees C. And then the temperature rises to 37 degrees C, and we're asked, well, what is the change in length of the streetlight? So we just need to use our thermal expansion equation here. The change in length is equal to alpha, which is the linear expansion coefficient, times the change in temperature times the initial length. And so we can look up the thermal expansion coefficient of steel, because we're told it's a steel streetlight. So that is equal to 11 times 10 to the minus 6. The change in temperature, that's the final temperature, 37, minus the initial temperature, 18. So 37 minus 18, that gives us 19, times the initial length, which is 7.6 meters. And so this is equal to 1.588 times 10 to the minus 3 meters. So this is equal to 1.6 millimeters, and that's to two significant figures, which isn't surprising because these are very normal temperature changes, and we don't notice the change in height of street lamps as they get hot. So we wouldn't expect this to be a big number. We'd expect it to be a small number like this one. Okay, this is problem 6. With this problem, we've got tea, which is made by mixing 520 grams of hot tea, which is essentially water. So that's 0.520 kilograms of water with an equal mass of ice. So the mass of ice is equal to 0.520 kilograms as well. And we're asked, what are the final temperature and fraction of the mass of ice remaining if the initial hot tea is at a temperature of, in part A, 90 degrees. So T initial for the tea is equal to 90 degrees. The initial temperature for the ice is 0 degrees C. Okay, so let's start by calculating how much energy we need to melt all this ice. Then if we have that much energy, we know it's all going to melt. So the Q needed to melt the ice is given by the mass of ice times the latent heat of fusion. So the mass of ice is equal to 0.520 kilograms, and the latent heat of fusion is equal to 3.33 times 10 to the 5 joules per kilogram. So solving this on the calculator, we get 1.73 times 10 to the 5 joules. So this is how much energy we need to melt all that ice. Okay, so if we now consider the water, we can work out how much energy it can release when it cools from 90 degrees to 0 degrees, and we can compare that to this number to see if all the ice melts. So the heat which can be released from the water is given by the mass of the water times the specific heat of water times the change in temperature of the water, which is equal to the change in temperature of the water is going from 90 to 0. So that's 90 degrees. So substituting in, we've got 0.520 times 4,186 times 90, and this is equal to 1.959 times 10 to the 5 joules. Okay, so in this case, the water can release more energy than is needed to melt the ice. So this tells us that all the ice is going to melt. Now, if we make the assumption that no heat is lost, assume then we can say the heat lost by the water, which is given by mass of water times the heat capacity of water times the change in temperature of the water, which is the final temperature of the water minus the initial temperature of the water. This is the 90 degrees, and this is whatever temperature it ends up at. Now, the ice itself gains heat as well. Once it's melted, it then raises its temperature from 0 degrees up to the final temperature. So we can write that as mass of ice times CW, because once it's melted, it's water, so it's got the specific heat of water. Now, the final temperature is the same as the final temperature of this water, but the initial temperature is 0, because this is as soon as it's melted. And then the ice also needs the energy in order to melt. So that's the mass of ice times L. And that's the latent heat of fusion. And this equals 0 because we're assuming no heat is lost. Okay, now we know that the mass of ice is the same as the mass of water. So this mass of water is the same as this mass of the ice, which is the same as this mass of ice. So we can just divide by that to remove it from the equation, just to simplify things a bit, because what we're trying to find is this final temperature. So what we can write this then as CWTF plus CWTF is equal to, I'm going to move this initial temperature, so temperature initial times CW, and then this LF over to the other side, which gives us that our final temperature is equal to the initial temperature times CW minus the latent heat of fusion divided by CW. So this is equal to the initial temperature, we were told was 90 degrees in this part, so 90 times 4,186 minus the latent heat of fusion, which is 3.33 times 10 to the 5 divided by 4,186. And solving that, we end up with 5.2 degrees C. Okay, so we've solved part A, we've worked out that all of it will melt and it will end up at 5.2 degrees C. In part B, the initial temperature of the water is now 70 degrees. So the heat needed to melt all the ice hasn't changed, but we can now calculate how much heat the hot water can provide, and that's given by the mass of water times the heat capacity of water times the final temperature minus the initial temperature, and in this case it's 70 degrees because the 70 degrees is cooling down to 0. So this is equal to 0.520 times 4,186 times the 70, and solving that we end up with 1.52 times 10 to the 5 joules. Okay, so this is less than the heat needed to melt the ice. So this tells us not all the ice melts. So we now need to work out how much melts. So once again, we'll assume no heat is lost. In that case, the heat from the water, which is given by MWCW times delta TW, and this delta TW is the 70 degrees here. So we've calculated this value here. This is equal to that, plus the mass of ice, which melts, times the latent heat of fusion is equal to 0. Now in this, up above, we had this term here. This related to the melted ice heating up. that doesn't happen here because not all the ice melts, so we don't need to include that term there. Okay, so we're trying to work out how much ice melts. So we have the mass of ice is equal to the mass of water times the heat capacity of water times the final minus T initial, and this is negative because we've moved it over to the other side, divided by LF. But the final temperatures, this is 0 and this is 70. So overall, we're going to end up with a positive number on the top. So then we substitute in, we've got 0.520 times 4,186 times 70 over 3.33 times 10 to the 5. And when we solve that, we end up with 0.458 kilograms, and that's how much melts. It asks us for the ice remaining, so the ice remaining is equal to 520 grams minus 458 grams, which is equal to 62 grams. So this is problem 7. So in this problem, we've got a copper block. It's initially at 300 degrees C, and then it's dropped into 1 litre of water. So the volume of the water is equal to 1 litre. So we know that water's got a density of 1 kilogram per litre. So this is equal to 1 kilogram of water. And the water is initially at 20 degrees C. And the water quickly reaches 25 degrees C. So the final temperature of the water is equal to 25.0 degrees C. And remains at that temperature. We can assume that there's no steam converted and that no heat is transferred to the bucket itself. So in part A, what is the final temperature of the copper block? Explain. Okay, so once the temperature of the water stops changing, that will happen when it's in thermal equilibrium with the copper block. So that tells us that the final temperature of the copper block must also be 25.0 degrees C. If they weren't at the same temperature, then the temperature of the water would change until they were. So part B, this asks us how much energy does the copper block transfer to the water. So the heat transferred to the water is the mass of the water times the heat capacity of the water times the change in temperature of the water, which is the final temperature minus the initial temperature. So we've got 1 kilogram of water. The heat capacity of water is 4,186. The final temperature of the water is 25.0 degrees C and the initial temperature is 20.0 degrees C. So this is 1 times 4,186 times 5. And solving that, we get 2,930 joules. Now, technically, we should actually give this to 2 significant figures, as this part of the equation here is only known to 2 significant figures. So this is equal to 21 kilojoules, and that's to 2 significant figures. Now part C then says, what is the mass of the copper block? Okay, so we know that this heat which the water absorbs comes from the copper block. So the mass of the copper times the heat capacity of the copper times the final temperature minus the initial temperature of the copper is equal to minus 20,930. And so we're trying to work out the mass of the copper. So rearranging this, we've got the mass of the copper is equal to minus 20,930 over the heat capacity of copper, which we can look up, and it's 390, times the final temperature, which is the 25.0 minus 300. Solving this, we end up with 0.192 kilograms. And so let's give that to 2 significant figures, 0.19 kilograms. Okay, part D then asks us if 3 grams of water is converted into steam, but everything else remained the same, what would be the final temperature of the water? Okay, so in this case, if we assume that no heat's lost, we've got the mass of the copper times the heat capacity of the copper times the final temperature minus the initial temperature of the copper. So this is the heat which is lost by the copper, plus the heat which is gained by the water to raise its temperature, plus the heat which is gained by the steam as it converts itself to steam. Okay, now to convert itself to steam, it needs to do two things. It needs to undergo this phase transition. It also needs to get up to that final temperature. So here we should have mass of the steam times the heat capacity of the water times the change in temperature. So the final temperature it gets to is 100, and the initial temperature is the initial temperature of the water. And that all has to be 0. And what we're trying to find is this final temperature. So we have the final temperature outside of mass of copper, heat capacity of copper, plus of mass of water, heat capacity of water, is equal to, now we're going to move every other term over to the other side. So we've got mass of copper, heat capacity of copper, times the initial temperature of the copper, plus the mass of the water, heat capacity of the water, times the initial temperature of the water, minus the mass of the steam times the latent heat of fusion of the the latent heat of vaporization. And then we're also moving this term over here, so that is equal to plus, it becomes minus when we move it to the other side, minus the mass of the steam times the specific heat of water times the final temperature, which is the 100, minus the initial temperature of the water. And so to get the final temperature, we just need to divide this by this thing here. So let's substitute in and divide at the same time. So the mass of the copper, that's 0.192 times 390 times 300, plus the mass of the water, that's 1 times 4186 times the initial temperature of the water, which was the 20, minus the mass of the steam, which is 3 grams. So 3 times 10 to the minus 3 times 2.26 times 10 to the plus 6. And then minus the mass of steam, which is 3 times 10 to the minus 3 times 4186 times 100, minus the initial temperature of the water, which is the 20. And then we need to divide all this by the mass of the copper, 0.192 times 390 plus 1 times 4186. So solving that on the calculator, we end up with 23.1 degrees C, which is equal to 23 degrees C to 2 significant figures. Okay, so this is problem 8. And in this one, we've got a skier. His clothing is 1 centimeter thick. His thermal conductivity, K, is equal to 0.040 watts per meters per Kelvin. His surface area is 1.8 meters squared, and his inner temperature, his hot side, his body, is 33 degrees C, and outside the air is 1 degree C. And we're asked in part A to calculate the rate at which body heat flows out of the clothing. So we can use P is equal to Ka delta T over delta X. So K, that's 0.040, A, that's 1.8, delta T, this is the hot side, the 33, minus the cold side, and delta X, that's equal to 0.01. I'm just converting from centimeters to meters there by dividing by 100. So solving this on the calculator, I get 230.4. So that's equal to 230 watts, and that's to 2 significant figures. Okay, now the poor skier falls into some water, and his soaked clothes have a new thermal conductivity of 0.60. So this is a higher thermal conductivity. So now we can calculate the power again. Is 0.60 instead of 0.04 here times 1.8 times the change in temperature, which is the 32. That's the temperature difference between the two sides, divided by 0.01, and solving that we get this is equal to 3,500 watts, so it's much higher. So if we divide this one by this one, we find it's around about 15 times higher than before, which is why he's going to end up so cold. So this is problem 9. So in this problem we've got 2 rings. The aluminium ring has a diameter of 16.2300 millimeters, and this is at 25 degrees. The copper ring has a diameter of 16.2250 millimeters, and again that's at 25 degrees C. And these are placed onto a ring stand, and the ring stand is made of steel and has a diameter of 16.2200 millimeters, and that's at 25 degrees C. So you can see at 25 degrees C, the copper ring and the aluminium rings fit onto the ring stand as their diameters are larger than the ring stand. And the question asks us if the ambient temperature drops by 25 degrees C, so these all now go down to 0 degrees C, do the rings still fit onto the ring stand? Okay, so what we'll need to do is work out the new diameter of each of the rings and the ring stands in order to answer this question. So the change in diameter of the aluminium is going to be equal to alpha of aluminium times the diameter of aluminium times the change in temperature. Alpha for aluminium, we can look that up, and that is equal to 24 times 10 to the minus 6 times the 16.2300 times 25. It's going to be a decrease because the temperature decreases 25 degrees. So this will be 9.738 times 10 to the minus 3 millimeters is how much this changes, and it reduces by that much. So the final diameter of our aluminium ring will be the initial diameter, the 16.2300 minus 9.738 times 10 to the minus 3. And solving that, we end up with 16.2203 millimeters. Now the change in diameter of the copper is equal to alpha copper times the diameter of copper times the change in temperature. The linear expansion coefficient for copper is 17 times 10 to the minus 6. The initial diameter of the copper ring was 16.2250, and this is times 25. This is how much the diameter will reduce. Solving that, we get 6.8956 times 10 to the minus 3. So the final diameter for the copper is equal to the 16.2250 minus 6.8956 times 10 to the minus 3, which is equal to 16.2181 millimeters. Okay, now for the stand, that's the steel. So the change in diameter of the steel is equal to alpha for steel times D for steel times the change in temperature. Alpha for steel, that is equal to 11 times 10 to the minus 6. The diameter of the steel, we were told, was 16.2200, and the change in temperature is 25. So this will reduce by 4.4605 times 10 to the minus 3 millimeters. And so the steel, the final diameter is going to be the initial diameter, 16.2200 minus 4.4605 times 10 to the minus 3. And so this is equal to 16.2155 millimeters. Okay, so 16.2155, that is smaller than both of these diameters here. So we're comparing this to this and this. These are both still smaller than this. And so since they're both still smaller, both rings still fit on the stand. Okay, this is problem 10. This is a fun little one. So we've got water flowing out of a tap. The initial temperature of the water is 20 degrees C, and it flows into a water bath. The flow rate is 0.020 liters per minute. So this tells us that the mass per second, which is falling into that, is because 1 litre is 1 kilogram. This is equal to 0.020 kilograms per minute. So that's over 60 seconds. And so each second we've got 3.33 times 10 to the minus 4 kilograms flowing into our water bath thing. Now, if we don't want the mass to change, we need this mass of water to evaporate each second. So we need 3.33 times 10 to the minus 4 kilograms to evaporate each second. Okay, so in order to evaporate, first of all, we're going to need to raise its temperature to 100 degrees C, and then we're going to have to put in extra energy in order to make it vaporize. So the amount of energy that we need to add is going to be equal to the mass of the water times the heat capacity of the water times the change in temperature of the water, which will be from 20 degrees up to 100 degrees, plus the mass of the water times the latent heat of vaporization. Okay, so the mass of the water that we want to evaporate is 3.33 times 10 to the minus 4. Latent heat, 4,186. The change in temperature, it needs to get to 100 degrees from 20 degrees. The mass again is 3.33 times 10 to the minus 4. And the energy needed for the latent heat of vaporization is 2.26 times 10 to the 6. Okay, so solving this, we need 864 joules. And this is how much energy we need to add to vaporize this much. So we need to add this amount of energy each second, as this is the mass which is being added each second. So the energy per second, that is just the power in watts. So the power we need to add is equal to 864 watts, and we should really give it to two significant figures, as the flow rate's only to 2. This thing is only to 2 significant figures. So this is equal to 860 watts. And so we've solved that problem.